Is that I put the 2003 modeling document up there when my team first published that in 2003. I don't think I appreciated at the time that it was a sort of a watershed event for the industry. It took a lot of convincing of GE management that going with open structures instead of we were doing black boxes just like everybody else. Proprietary, if you want the model, you need to sign your life away and your firstborn child and all those other things. And I made the case in 2003 to GE management that if we wanted wind power, wind generation, to play more than a bit role, then the industry was not going to accept that, and that they needed to understand what the equipment was doing and create talk in the language of the system planners. So that very first structure was quite consciously developed to look as much like a synchronous generator as we could make it, to ease the fears of the utility world. So it had a generator block and a thing that masqueraded as an exciter block and a thing that masqueraded as a governor block. And the fact of the matter is everything inside was completely different. But that worked well for the industry, and it's carried us a long ways forward. And it's carried it a long ways past me. Fortunately, I got smarter, younger folks at GE that are supporting the development of the next generation, but it's been a wild ride. I think the evolution aspect is kind of important for this narrow subset. It's a good follow-on to Paul's talk. And this is a little context. You've heard other talks already in this meeting. Voltage control from wind plants, 14 years ago was sort of a novelty. It's not now. It's required in most systems. Almost all grid codes, the exact details of what can be done, what are asked for vary from grid code to grid code and utility to utility. And one of the things that is the topic of my talk today, and again isn't news I think to most people in this room, is that the power electronics in wind allow things to be done very, very fast. Very fast. And there is a risk that I'm going to talk about a little bit today, in that the natural reaction is faster is always better. And that isn't always true, and there's some cautionary notes in my talk here today. So first, to get you a little bit calibrated, and those of you that know me and have seen me speak over the years probably are sick to death of seeing this slide, because I've been using it for well over a decade. And this is field measurements on the left, and it's an eye chart, but I'll walk you through it for a second, of the behavior of a 162 megawatt wind plant out at the end of the end of the end of a system in the western United States. So the 162 megawatt plant's pretty big. It's connected by a radial, this drawing notwithstanding, a radial 75 kilometer 230 kV transmission line to a line that is radially connected by another 100 kilometers to the rest of the grid. So this is out in the middle of nowhere, and the requirement was for voltage control to manage the variation that came with the wind speed. Okay, so this is an hour measurement. I know you can't read the axes, but this is an hour. This is a swing of about 30 megawatts, so it's a fairly ugly hour. Okay, and the blue line is the voltage at the point of interconnection, 75 kilometers away from the wind plant. One division on that, so this is US 60 hertz system, we use 230 kV. So one division, which I hope you can see, is 1 kV. Okay? So that little furry blue line there has variations on the order of 1/10 of 1%. All right? The voltage control is perfect. All right? I used to make a really big deal out of this a decade ago when people didn't believe you could do it, but we've moved beyond that point. All right? So anybody that says you can't get good voltage control when you have wind plants is stuck not only in a time warp, they're not even in the right century anymore. All right? So it works well. And these controls take advantage of the power electronics, but they are not tremendously aggressive, because the reality is that, you know, air mass is a state variable. The fluctuation from wind is not super fast in the context of grid events, which is why some of the grid codes now and some of our customers are asking for very fast response. And so I highlighted this may. You may need very fast, okay? It's not because it's wind, and it's not because the wind is variable, but it may be because of the topological constraints on the system, where the wind is, and maybe what the wind has displaced, all right? So that's really the question. So, but it is quite important. Voltage regulation and reactive power control does not happen in a vacuum. There is a closed loop response with the grid, and as the grid gets weaker, the gains go up. So you have to take care of that. Some of you probably have seen a paper I wrote a few years ago about coordinating between multiple plants. If you have multiple plants that are in close electrical proximity and you don't coordinate the regulators, you know, this is controls 101. It's not because it's wind, it's because you didn't do your homework, and they can fight with each other. So don't do that. That's a lecture for another day. All right? But any case, but there are things, they're real life things, right? A wind plant might be spread across several kilometers, and you have common signals. So you start cranking the gains up, the latencies, the time it takes to communicate and be confident that you've properly communicated with the wind turbines start to impinge on your control bandwidth, and you get you have some risk of stability. So careful what you ask for. And so I'm going to give you a little. This is a little context, and this is a field test. It's not particularly important, other than that this is a typical commissioning test for a wind plant, where it comes with factory set settings, and then you go along, and part of the commissioning exercise is to give steps in voltage reference and make sure you get nice, stable, well-mannered, no overshoot. Right, so that's the reference step, and that's the Q command, and the other one is the Q. And I can't remember why they're displaced. There's some good reason for that in this. I think maybe it was just to make it readable so you could see the two. So this is a really nice control response. No overshoot. It goes right where it's supposed to. It does its thing. And this is perfectly fast enough to give you that kind of perfect voltage control. All right? But if you start cranking the gains up, say, well, you could do this fast. You got power electronics. Let's go, you know. Make it zippy. You can get in trouble. So that's what this is simulation work. So I'm going to go on to field measurements. So here we are in a world where we've got a customer that has said you shall have a control that goes where it's supposed to go within 1 second, regardless, okay, of the operating condition. So 1 second, right? You cannot do that with a synchronous machine. Nobody's ever built a synchronous machine that has a 1 second response. But because it's wind or solar, what the heck? Let's crank up the requirement. Give me some more gain. All right? Well, this is the kind of thing that happens to you, and I'm not going to drag you through all the details, but what you got here is when the system is stiff, you need a lot of gain to move it. But when the system is weak, the closed loop gain goes out the roof and it goes unstable. That's the narrative that goes with that thing. Bad outcome. All right? So you start using more sophisticated controls that have fancier leads and other kinds of things, and you do better. And you still get the corners bite you. All right? So then you come along and you start having topological changes to the controller with adaptive gains. Oops, sorry, Paul. We just damaged the generic wind turbine excitation models because now we got adaptive gains. Doesn't fit. Okay, so we're still learning, but you can get there, right? So this is a very nice response with basically no overshoot, and it's doing what it's supposed to, and it was no picnic to get there. All right? So the customer believes that they had a legitimate systemic need for this very, very fast response, and we got there. So, and then here's some field tests. All right, so we're banging the system. So this is the total VARs. So the way you want to read this, this is 1 second across here. That's the stimulus, and that's the reset. So the response is indeed 1 second. Right? So there's a little bit of droop going on in there. So that the fact that that's not exactly there is not a violation of the objective. So this is up, this is down. We did it. Okay? So you can get there, but you really got to be careful. But this is an example of how you do a field test for this sort of thing, where you bang the system around by doing switching operations. So one of the best ones you can do is switch cap banks. Okay. This is the first generation and the second generation generic model, so I don't have to say anything more about that because Paul covered it. You see they have gotten a little more complicated, and we've been there. Again, this is slightly U.S., slightly North American-centric view. I have that, even though the discussion here isn't really aimed at my U.S. customers. So our reliability entity requires that every generator on the power system be tested every 5 years. So there's these 3 mods, and those are modeling validation requirements. It's a statutory requirement. You got to go out and test the plant to make sure that the generator model is right, to make sure that the excitation system model is right, and to make sure that the governor model is right. And that standard has been updated recently to have no exceptions. So solar plants, wind plants are not exempt from this rule, and you got to do it. And there's a whole bunch of good reasons for doing that, which I list up here, but notice that they don't include compliance. U.S. grid code has very little quantitative requirement for speed or other kinds of things. Basically, plus or minus 0.95 power factor at the point of interconnection and fault ride-through capability. And otherwise, the rules say you shall provide dynamic voltage regulation, but it doesn't, it's relatively silent. That's a cooperative arrangement that has worked reasonably well in the U.S. So to do model validation, you sit here and you dump all the model parameters into, this is the GE model. It's very similar to the WEC model. And you go out and do tests and you lay one over the other. You've seen lots of these things. That's a nice test right there. I don't think I need to talk about this equivalent here at all. But there are some things, like thou shalt go forth and test the plant. Well, Mother Nature isn't terribly cooperative sometimes, and sometimes the grid people aren't very cooperative. So the first thing you got to do is make sure that you have a substantial amount of wind, and it's better if it's pretty steady, because if the wind is moving all around, then you have active power variations that cloud your results. You got to be careful. All right? I got this high gain and this tremendously capable control. If I go out to test it and I wallop the thing, I can easily drive the grid voltages someplace that is unpleasant, or it can fight with other equipment. So these things have to be done rather carefully and in coordination with the grid operator. So you've seen that. And you know, these things all start to get a little old. You can get the model to match. So this is a very typical kind of U.S. view of the world. All right? We don't have any standards. NERC does not have standards that say quantitatively this is a good match. It's kind of like the U.S. Supreme Court in pornography. You know it when you see it. So everybody looks at that and says, yeah, it's a good match, it's a good model. You know? That's frankly the level of sophistication, and it has actually served us pretty well. Here's another test, so a similar sort of thing. So this is my, and I got a barb out for Australia, but it's a learning thing. People love to be quantitative, especially, you know, I don't know. There's some cultural things there, so I won't pick on any particular culture. But the AEMIL requirement says that the model shall replicate the required performance and the demonstrated performance within 10% at every time step. All right? Say, oh, well, you know, 10%, what's the matter with you guys? Can't you do that? It's like, holy smokes, that is really hard, especially around the corners. And what happens, and what has happened to us and other members repeatedly, is you end up having to add bells and whistles and blocks and crazy crap to the model to capture minute and utterly unimportant junk that goes on around the corners. and it doesn't increase the system reliability. It doesn't improve the system performance. It doesn't pay any rent to anybody except the people that are in the business of writing models and making them more complicated, right? So maybe we should like it, right? But we don't really. So don't do that. So there's a real cost. And some of these tight restrictions, the manufacturers have to get into the knickers of the model and tweak them, because you cannot get there from here otherwise. So in conclusion, you got to be careful about mandating tests. You need to have some flexibility to get Mother Nature to behave, right? You got to be careful about really walloping the system, the grid, when you're doing the tests. You can have some very unpleasant outcomes. You got to have a conversation about what's good enough, and you already heard my bias. Everybody should sit around with a pitcher of beer and say, yeah, it looks good. All right? And avoid requirements that are unduly strict. Now, we aren't advocating being sloppy. You're interested in the reliability of the system. You are not interested in an academic exercise in matching curves. This is all about reliability. This is all about value to your customers, and it's all about economic grid operation. It's not about a science project. So get it right. Thanks.